All right, so quick review. Working with probabilities in the Z distribution, and note that this is using table A and B in your tables. Note that you can get table A and B if you've got the little cardboard thing still in your book. If you pull that cardboard thing out, that will always have table A and B in it. Note that table A and B are also the very first page in the cover of your text as well. Works just as good. Strongly encourage playing around with this thing though, because this thing, right, the nice thing about this cardboard fold-out thing is that not only does it have all the tables we work with, but if you flip it over, it's got all the formulas that we've ever worked with in any of the chapters as well. So it's kind of a nice reference guide to play around with, so that you don't necessarily have to have the book with you all the time. All right, so what is the probability that Z is less than 1.43? .9326. Just get comfortable looking up the numbers inside of the table. Again, it's just kind of getting used to it. No, folks, does it matter whether I put in a less than or equal to into my inequality? No, it makes no difference whatsoever. Okay, so whether there's equals in the probability thing doesn't matter. So whichever way, don't worry about it too terribly much. Because in a continuous probability distribution, 1 point makes no difference, okay? Because there's an infinite number of them, so 1 won't make a difference. All right, how about probability that Z is greater than 1.18? What was that? Let me turn you up a little bit.
0.119.
Note I asked for greater than, folks. If you just look up 1.18, what's it giving you? Less than. So please be careful with that one, okay? When dealing with greater than, you have to use 1 minus the less than. That's just a standard process you got to get used to. So what is 1.18? Is that the 0.88? 8808? Is that what it was? 10? And so what is 1 minus 0.8810? 0.1190. Again, just be careful with that. And what happens if I ask you to find a probability for Z's between two values?
Take the larger one and subtract the lower one from it.
Yeah, This is the probability that Z is less than 1.26 minus the probability that Z is less than negative 0.15. So what is Z less than 1.26? Anyone? 8962. And what's the probability that Z is less than negative 0.015? 4404. And then just be careful punching into your calculator to get the actual probability. 4, 5, 5, 8. Alright. Not bad?
Could be worse.
Should I do an absolute value one, or could you handle that? Should we do one just to be safe? Okay, let's do it. Alright, so let's try, what's the probability that the absolute value of z is greater than, 2.08? Again, note that that's greater than. And remember what absolute value means, okay? And sort of the way I like to remind students of how to deal with these problems is remember that this is all done through a probability distribution graph, right? Here's 0, and at the inflection points are 1 and -1. And so the stuff where z is going right and left here, and the probabilities are going up and down, so the probability that z is greater than 2.808. Here's 2.08. I'm looking for this tail, right? And note that since it's absolute value,
It's always positive.
it's always positive, so when you get z's that are more negative than that particular value, you need to have those as well, right? You need to add these two tails together, right? Because you've got the positive numbers of z that are greater than 2.08, so 2.1, 2.15, etc. But then, since you're taking the absolute value, once you get past negative 2.08, it becomes true again, right? Because negative 2.1, the absolute value of that is just positive 2.1, so therefore it is greater than as well. Both of these tails of your probability distribution should be added together. So this equals the probability that z is greater than 2.08 plus the probability that z is less than negative 2.8, okay? This piece is here. That piece is over there. Okay? So every one of these probabilities has a picture that's similar to this. Okay? And you should be able to draw the picture as well as calculate the values for any of these, right? They should sort of go hand in hand. Again, please be careful with the probability that z is greater than 2.08. That's greater than, not less than. So 2.08, wildly annoying number. Less than 2.08, 2.08, or 0.9812. Plus negative 2.08 and note what does 1 minus 0.9812 equal? 0.0188. And that's because you guys know another thing about this bell curve, folks. it's symmetric. When you fold it over 0, the two sides of the bell are exactly the same. So whatever value you get for here, this side, since it's the symmetric piece of it, has to be exactly the same. So technically you should only have to ever calculate one of them, and then just multiply by 2, okay? Regardless though, either way you go about finding the answer is perfectly okay. In the end, 0.0376. Hadn't made the last step.
Why did the one last?
That's fine. Either way. Alright. Not bad? Look it up. You can make sure you know what you're doing. Alright, because I mean we're just building on it from here, folks. I mean this is the easy part of it. We're going to be using these sets of tables over and over and over again from here on out. So if you don't get it now, it's just going to be much, much, much worse later. So if you're not seeing it, please let me know so that we can try some more problems and make sure we get it. All right? All right. Okay. So. All right, so let's go back to working with a regular normal distribution instead of the very specific standard normal distribution that we are working with, okay? Again, please remember that whenever we talk about standard normal distribution, think z-scores, okay? Standard normal is z. Normal distribution is just a regular old problem that's got a mean and a standard deviation for a normal distribution, okay? Okay, so. So if I have a normal distribution where the mean is, let's suppose the mean is 15.0, and the standard deviation is 2.8. So let's suppose that, again, whatever this measures, I have no idea, but
Is that a medium or is that a mu?
that's a mu, and it represents the mean for a population, okay? Okay? So mu is mean, sigma is standard deviation, right? Okay. So what is the probability that I grab a random item from the population and its value is less than, well, let's make it relatively easy to start with, 14. So in 6.2, we were talking about calculating probabilities for picking z-scores from a standard normal distribution where we had normalized things into z, okay? And what I want to do here is to say, wait a second, what happens if I go back to a regular old normal distribution, not the standard one, can I do the same thing? And the answer is yes. All right? So, and the key here is realizing that we're working with x's now, and it's x because we are in just a generic normal distribution, okay? And what we want to do in order to make this work is to translate it back into whatever a standard normal distribution is, okay? So what we do is use fact that z equals x minus mu over sigma to translate this into a z. All right? So we are going to translate the x into a z. But the way we are going to do it is realizing that this is an x, okay? So to make this 14, which is an x, into a z variable, I have to apply this. So I'm going to say this has to be 14 minus whatever the mean is, 15, and divide by whatever the standard deviation is, 2.8. And that's the translation. It's just basically saying if you want to stick an x, you translate it to z and then work with it just like it's a z problem. Okay? So get out your calculators.
Pretty easy.
And what is 14 minus 15 divided by 2.8?
0.3 or negative 0.357.
Negative 0.357. Please note, folks, you should round all of these numbers to hundredths because the table in A and B, all of your values are rounded to the hundredths. So negative 0.37, you said, or 6?
It's 3.5, so it'd be 3.6.
357 or whatever?
Yeah, it's 3.57.
Yeah. So round it to 0.36. And then you just use the tables to look that up. So using table A, what do you, yeah, it is table A, what do you get?
0.3594.
So that translates all the way back up to what the probability of picking some value from this particular distribution and having its value being less than 14.
That's all there is to it.
Yeah, that's all there is to it. I mean, it almost seems like it's too easy, and let it be too easy.
Change it to a percentage, leave it at that.
You can do either thing. Usually you leave it like this, but every now and then the homework will say, what's the percentage that I picked this, and just, if it asks for a percent, convert it. Normally they'll leave it as a decimal. And I generally prefer it as a decimal, so I would recommend leaving it that way, but there are a few homework questions that specifically say, write it as a percentage, so if you would, do that for those. Alright? Not bad? Alright, so all of the games that we played with Z, we can play with X as well, okay? So, what is the probability that I choose a number between 13 and 16 in my normal distribution? And you just have to do the exact same thing, except do it to both sides of the inequality, convert it into a z, and then look the numbers up the same way we've been doing back in 6.2. Okay? So it is a matter of just sort of making that translation into z in order to find the probabilities that we're looking for. Alright? So do the same thing, right? Subtract the mean, divide by the standard deviation, convert your x into z, 16 minus 15 over 2.8. And again, round all of these things to hundredths because that's what the table does. You can only read down to the hundredths, at least for us. So what's 13 minus 15 over 2.8? 7, 9?
No, not 171.
7, 1. The other 9. 1. And what, 16 minus 15 over 2.8? Or 1 over 2.8? And then just remember how to deal with this on the z side, and you're all good to go. Right? And remember, probability that z is less than 0.36 minus probability that z is less than negative 0.71. Is that what it is?
Mhm.
Yep. Negative 0.71.
2389.
2.89. Do the subtraction. Point 4017. Is that what it is?
On the dot.
All right.
Yeah, you need a calculator.
That hurts. All right. Not bad. Okay, so now let me make it just a little bit more challenging and a little bit more real. Okay. What is the probability I pick a number that is more than 2 standard deviations Uh-oh. No.
Did Skynet become self-aware? Oh, that's not good.
That was crash and burn, folks. Uh-oh. Yes, I would like to recover, please.
We
Okay.
had somebody invented self-recovery for computer programs, you know?
Oh, that didn't recover very much, did it?
Nope.
Son of a gun. Huh?
That thing went out of the recording.
Did that crash too?
I would check it, because it went out, you're like, usually in the corner, you have like the black recording box, and it's not there, so that's why.
Oh, looks like we're still going.
And then they already got some of it already.
That's true. It's still on the video if you guys want to watch the video. All right. So where was I?
Probability of picking a number more than 2 standard deviations.
Oh yeah. Probability picking a number more than 2 standard deviations from the mean. So this is a more traditional sort of statistics type question to ask. How often do I pick something that's 2 standard deviations or more away from the mean? And note that 2 standard deviations means that something rare is happening, right? Remember that 95% of all of our numbers fall within 2 standard deviations. So this is this is a rare event. How often does it happen, or what's its probability of happening? All right?
0.0456.
Why?
Because you take the number for a z-score of less than 2 and double it. I'm sorry, less than -2.
Less than -2. Okay, so here's sort of how it works, right? Here's a quick way of looking at it. Ben's taking the shortcut. He's cheating a little bit. All right? We're translating this stuff into standard normal distributions, right? We're always going to take these x's and flip them over into z's. And the cool thing about z's is that they're all based off of these number of standard deviations, all right? So for our problem, where I had mu equal to 15.0 and sigma equal to 2.8, what numbers are more than 2 standard deviations away from my mean? But they're 2 standard deviations, not 2. What are 2 standard deviations? What are 2 of those?
5.6.
Why is it 5.6?
That's 2 of that.
Yeah, because that's 2 times 2.8. So what I'm looking for is x is greater than 15 plus 5.6, right? This is 2 standard deviations. That's 2 standard deviations on the positive side, or plus the probability that x is less than 15 minus 5.6, because that's 2 standard deviations going to the other side. Okay? So for our problem, right, where we're working in x, here's 15, this is 17.8, this is 12.2. If I go 2 standard deviations, 20.6. If I go 2 standard deviations, what is that? 9.4? 9.6?
Sounds about right.
It is 9.4?
I can't keep track. 12.4, 9.4. I was right the first time. It's a 2.
Correct. So I'm looking for things that are either more than 2 standard deviations away or less than 2 negative standard deviations away. The same sort of side, that tails concept. Calculating tails is a very common occurrence when we're working in statistics, so prepping you for this is good. And so here's where this translates into, right? The probability that x is greater than 20.6 plus the probability that x is less than 9.4. That's exactly what the picture shows. That's what the numbers confirm. Okay? And the nice part about it, once you start to do this, is that once you start crunching these into z's, you'll see what Ben was talking about, all right? So these are x's, right? We need to convert these to z's. So this is the probability that z is greater than 20.6 minus 15 all divided by 2.8. Subtract the mean divided by the standard deviation plus probability that z is less than 9.4 minus 15 divided by 2.8. That's a decimal, I swear. And nicely enough, when you do 20.6 minus 15 and divide by 2.8, what do you get?
5.6. I'm sorry, 2.
5.6 divided by 2.8. 2, right? And that will always happen. If you do 2 standard deviations, the whole point is that you're really just saying z is 2 standard deviations away, so your z value will be 2. And then likewise on the other side, when you do 9.4 minus 15, you get negative 5.6. Divided by 2.8, you get negative 2. And now you play the same sort of game of making sure those numbers add up. And one of the things that you will want to try and get in the habit of, due to symmetry, so the fact that you know greater than 2 is the same as less than negative 2, that means you just have to look up one of the numbers and then double it, okay? Use symmetry to your advantage. It's a wonderful, nice tool, and it makes a lot of these calculations a lot easier, all right? And, I'm sorry, what was negative 2? 0.027.
228.
228, sorry. And then double that stuff. 0, 4, 5, 6. So it's rare in a normal distribution to pull a number that's going to be more than 2 standard deviations away. Less than a 5% chance from that happening. Which makes sense because that's what it means to be normal, right? Is that stuff is mostly bunched right around the middle near the mean, and there's only a few of them that are out there on the edges, and so you should not expect those probabilities to be very high. All right.
How did you get that number?
Which number?
0.028.
Well, the probability z is less than negative 2? 0.0?
Okay, but then why did you times it by 2?
Because this number, these two values, they should be equal. So you can use either one that you can look up. That's going to be easier. And since the greater than one, you have to do 1 minus in order to find, don't do that one. Do 2 times the other one.
That's what I was working on.
But yeah, that's that whole symmetry concept. Okay?
Okay. I'm just trying to understand.
Oh no, that's good. That's what.
So, more than 2 standard deviations, you went to more standard deviations from the first outside?
So I started in the middle, right? I started at the mean, and I went 1 standard deviation, which is 2.8. So I just added it. This is just the first standard deviation,
Okay.
right? First sigma. This is my second sigma. Yeah. Just add in the 2.8 as we go. Monroe folks? Yeah? Heidi, this looks like she's in shock. All right. Are we good? Okay. So, let me do a book problem just so that you can get a feel for how the book asks these types of questions. All right, so. What did I assign? Like 2, 4, 6, 8, and 10, all the evens or something like that?
4, 8, 12, 14. Or sorry, like 4, 6, 8.
4, 6, 8, and 10? Okay, so yeah, basically just. Okay, note that folks, on those homework problems, 4, 6, 8, and 10, each one of them have 4 parts. So that's really 16 questions, not just 4. It looks like it should be really straightforward, but every one of them has A, B, C, D, so be careful. Yeah, and those of you who've had me before know that I like those kinds of questions. I love A, B, C, D. Yeah, I know a little statistic, yes. All right, so let's see. How about we do number 5, okay? All right, so we're looking at some data from the Chamber of Commerce, and it says that the weekly wages of office workers are normally distributed and have a mean of $700. So wages are normally distributed. And note, folks, for right now, in order to do any of this stuff that we're doing, we have to be normally distributed, okay? We'll get into chapters 7, 8, 9, and 10 where we maybe don't have that, but for right now, technically 271. And the mean is $700 per week. So office workers have a mean of $700 per week, and their standard deviation is $50. So they made the numbers relatively nice. If it were me, I would probably say that the average wages were like $684.62, and the standard deviation would be $41.33, so that you really get to grind the numbers. You know, real fun, annoying numbers.
Is that what we're gonna look forward to on the midterm?
No, I'm not that much of a jerk. I mean, I'm close, but not really.
What is our midterm? It's gotta be coming up pretty soon. We have like.
Yeah, it's like a week and a half.
What?
Yeah, it's the week before spring break.
I am so not ready, but all
I thought spring break was like not
Do
until
it.
March
How long is
16th.
spring break?
It's like
Spring break is like in 2 weeks, right? Or like a week and a half?
right. March 16th?
Yeah, March 16th, right?
Yeah.
So it's a couple of weeks.
Yeah.
So it's gonna be, we're gonna have to do it over spring break?
Well, no, you're gonna do it during the week before spring break.
Oh,
The 16th through, the 17th through the 25th.
I will give you the midterm exam on that Monday, the week before before spring break, and you have all week to get it done.
and we won't have homework to do that?
No homework to do during that week,
No class.
and essentially no class either.
Oh, cool. I was just joking about that. All right.
Wait, what are we doing?
The week before spring break is the midterm week. So I'm gonna give you the midterm on Monday. And you guys just basically work on it for the rest of the week. And what I say is that if you have any questions, you can come to class and ask questions, and I will guide you on the midterm.
Wasn't that
So,
5 days?
but you don't have to show up for class if you don't want to. But if you'd like some guidance, it might be to your advantage
What
to
day
show.
is it?
It'll be due
That Thursday?
oh no, like Friday or Saturday or Sunday or Monday. Or, if you want to keep doing it into spring break, I'm okay, but I would advise against it. Yeah, Haley?
Oh, is this online or is it like a physical packet or something?
Both.
Both?
Yeah, I will print it out and give it to you, and then I will also have it online that you can grab and use as you wish.
Oh, okay.
So if you actually don't show up to class on Monday during midterm week, that does not excuse you, because the midterm will be online and you can go get it. And
What's the actual due date?
before the Monday after spring break.
How would you just get it to you?
Scan it in,
Scan and email it to me.
mail it.
The school would be
Okay, make it due the Tuesday after you get it. You get one day to do it, whatever. I don't
I'm just
care.
saying, I don't have to
As long as
scan
you
it
get it
all,
to me
how do you do
before
that?
spring break is over, it's okay. So if you really wanna work 2 weeks on the midterm, you can. I'm willing to let you,
Technically, you do have a scan.
but you don't, I would hope
Or
you,
you can take pictures of it and send it?
yeah.
That's not a scanner though.
It's
I know,
still
but
technically.
waste a time and space, don't do that.
Oh, okay.
But, I mean, it works, it's okay.
Yeah, I was about to say.
And the problem with it is that when you take a picture, it's not very clear.
Yeah.
But, I mean, I am letting you know that technically, if you wait until literally the last day of spring break to turn it in, I will be okay with that, alright? I mean, I will warn you that I'm going to Vegas for the first half of spring break, so you can do whatever the hell you want, I'm not gonna know my name, so.
Weren't you the one who
Kicked out in
spent the
jail.
first half of this class telling us not to go to Vegas?
Yes, exactly.
Just
But-
don't gamble. You can
But,
still
but
go to
if
Vegas.
your brother-in-law goes to Vegas and gets a free comp room at Caesars every time he goes, and he
Oh,
invites
that's
you,
Often, then.
you go. He's at a wine conference there, and
So
so.
Vegas is a rough place. You're gonna need somebody to watch your back.
Gotcha.
I love Vegas. I don't usually gamble all that much, but I love going and just watching people. And I love watching the people that like play $10,000 worth of chips on the table, and I'm just watching them going, yeah, that's a happy year for me.
I'd be thinking, why are they doing to get that money?
Yeah, I don't wanna know that.
They do that up north. Like we played roulette and one dude put down $250 on one thing and I was like, lost it all. And walked away, got more money and came back.
Jesus.
See, this is why it makes me nervous to go to casinos. But I love going because the people watching is awesome. And I do like to figure out the odds in my head and think, well, what's the proper bet to make at this point in time? And my bets are like between $1 and $5. These guys are betting my paycheck at once, and I'm just like, yeah, no thanks, man. But it's fun.
We'll see them on like the scanners, we're not allowed at like hotels.
I have been kicked out of a casino before for card counting.
Really?
Yeah, because I was trying to do the whole counting cards at blackjack, and so I was sitting there keeping track with one hand the number of cards that are 5 or lower, and the other hand the cards that were face cards or higher.
Right, I was just gonna say. right?
Yeah. Because I wasn't trying to hide it, I was literally doing it on purpose. But I wasn't changing my bet ever. Right? I was still.
And they still kicked you out.
They still kicked me out because they could
Makes no sense.
see I was
It's
counting.
still not, they
Right,
don't
you
allow
should
it.
have been.
But I'm like, if you're not taking an advantage of it, it doesn't matter. I was just trying to keep track of it, and so I was, But yeah, they came in and excused me from the table, and I was like, I'm like, did I ever change my bet? It's been $5 every time because that, I only got like 50 on the table, so, I can't all of a sudden just change it to a $200 bet. 'Cause-
Do they give you your money though?
yeah, no, they didn't. Yeah, no, they didn't. They give you your money, otherwise
They don't steal your money, you kick you out.
Yeah, they just kick you out. That's it. And they didn't kick me out permanently, so I was happy with that. 'Cause in theory, he said your picture is now on file.
It just means when you walk in, those cameras are gonna be watching you a little bit closer than everybody else.
Scanning everyone.
Oh, he just scratched his nose, kick him out again.
No, they don't like kicking you out because if they do that, then they can't steal your money.
That's absolutely right. They want my money. I mean, even if it's $50, they still want my $50, right? All right. So anyway, sorry. All right. So first question says, if you choose a worker randomly, what is the probability that your wages are, of that person is less than $600?
0.0228. It's still on my
Why are you in
calculator.
this class?
Why is it still in his calculator? Because what do we need to do? We need to figure out the probability that X is less than 600. So what do we do to convert that into a Z? Strike that, reverse it. This is the probability that Z is less than 600 minus 700 all over 50. And what is 600 minus 700?
You lost me.
It's on the app. Wait, no, that's a negative one.
It's negative 100. What's negative 100 divided by 50? Negative 2. And what did we just do in the prior problem?
No, I see why it's still in this calculator.
What was it, 0.0188? Is that what it was?
228.
Is it 228? All right, so how about the next one? What is the probability that the wages are greater than $810? Note that this one's greater than. Convert to Z the same way.
Is there any problem with just looking up Z values less than the negative version when you're looking for weighting?
No, that's absolutely what you can do. And here is a neat little trick, folks, that Ben was just trying to point out a little bit ago. Note that this is the same as the probability that Z is less than negative 2.2. So greater thans you can convert to less thans by multiplying by a negative 1. And if you think back to your college math class, when we were doing inequalities, when you multiplied or divided by a negative number, what did it do with the inequality sign?
Flipped it.
It flipped it, and that's essentially exactly what we're doing here, right?
So that'd be the same as just minusing it from
Yep.
1. Okay, that's easier for me to remember than.
Lost on that one?
You can still do 1 minus the probability that Z is less than 2.2. These two things are the same. They will always wind up being the same. That's the whole idea behind that. And again, that's using the power of symmetry in the normal curve, right?
But do we need to find the negative?
You don't have to. You can do the positive and do 1 minus if you wish. But if you just look up the negative, you're done. That's it. So that's why you might want to do that, because then you don't have to do the 1 minus crap, right?
It's so much easier than doing that 1 minus crap.
Right? And again, that's purely from the symmetry, folks, right? Here's 2.2, we're looking for greater than. Here's negative 2.2, this is less than. These two things are always the same due to symmetry, right? And that's why it works. So, whatever you got with that, what did you get with this one?
0, 1, 3, 9. 1, 0, 3, 9.
All right, again, nice tips and tricks to make this easier. Indeed, these are great. I love this page, man.
All this information, I feel like I'm never gonna use it again.
Oh, yeah, you will. If you do any probability, you will. If you do any statistics, you will. And the main reason that we're doing this is not that you will do this again, but that this naturally leads to the more complicated things that we're gonna do later on. And if you don't understand this, the complicated things we do next will take your mind and blow it into next year. And that, we wanna try and avoid that if at all possible.
So
That's
very much in the
720
future.
or 770?
770, sorry.
Oh, that's
So very much we're gonna have an aneurysm in the future.
No, it's okay, yeah.
So, if the wages are between those two numbers, that's the probability that 620 is less than X, is less than 770. And again, translate, right? Get all the zeros in there.
Are you ever, like, I don't know, you do a lot of the common, like, same direction. Will those ever be flipped more than anything, like,
No, that doesn't
No.
make sense. No. To have these go the other direction, that doesn't make sense.
that would be finding Z basically then, right?
We'll get to that next chapter, or next section.
Even if you're writing it from like the Z standpoint, like, would you keep it Z, you keep it Z is, less than 620 or minus 700?
No, technically it's greater than.
Okay, just making sure, because I was a little bit confused last week on that.
Yeah, no, it's just.
Just it seemed like they were just staying the same, like, but it says there in the formula that it's greater.
Yeah.
Okay.
But it's, this value is less than Z, which is the same as Z being greater than whatever that value is.
Okay, yeah, like I said, I was just a little bit confused last week on that part, so,
Yeah.
or not last week, earlier this week. But, alright,
So whatever that worked out to be, 80 over 50.
I did too much talking.
Is that 80 over 50?
So would you multiply that 1.6 by negative 1?
No, because this just translates straight. Probably that Z is less than 1.4 minus probably that Z is less than negative 1.6, straight up.
Okay. Got it. So that's where it would throw me off, I'd be putting Z is greater than.
Right,
Oh,
yeah,
okay.
immediately.
Yeah.
Yeah, no. So this translation for in between always works this way, okay? That's just always doing, okay? And there's no real trick about it. The only time there's ever really a trick is if the two numbers on each side are the same absolute value. So if they were like 1.4 and negative 1.4, then we could potentially do something to make it easier. But if the two numbers are different, you just have to do it the long way.
So for
Okay.
greater than, it's the 1 minus the P, Z greater than.
Yes. If it's greater than, it's 1 minus the probability of less than. Or you can just do the probability of less than the negative. But these are all straight less than, so you can just look them up on the table. So what's 1.4? What was that?
0.9332.
9332. And what was negative 1.6?
0548.
And subtract.
So
870.
he went from being greater than to being less.
Yes.
We just subtract
Mhm. And the idea, right? If you look at the picture, here's negative 1.6, here's 1.4. What I'm looking for is this, right? That's what I want. And this one is 1.4 and everything to the left. So I need to take this tail off. And so that's why I subtract the negative 1.6, because the negative 1.6 is everything to the left of there in order to limit my probability.
The exam, or midterm, whatever you wanna call it, are we gonna have to draw the bell graph?
Probably yes.
The
How
number for
great
.14
are
is
they supposed to
actually
be?
.9192.
Oh, 9192.
Yeah, 9332 is for 1.5.
Okay.
Are you gonna like give out points if our bell curve was stupid?
No.
Okay.
Come on, look at my bell curves. Do my bell curves
Yours
look
look
good?
like a bell curve, mine go up and then slants like at a slow slope.
You'll get used to it. The more you draw them, the more you'll get better at them. Swear to God, folks. It's like drawing straight lines. Whenever I teach every semester, when I have to do graphing lines, the first 2 or 3 times I draw a straight line, it looks like this. Right? That's a straight line to me. But after you do it 4 or 5 or 6 times, then you can actually start to redraw a straight line. But
Okay, so you're not gonna be the teacher who takes out quarter points if the sign curve looks wrong?
no.
Thank you.
What if we make it upside down, sideways?
If you draw it like this, okay, then there might be an issue.
I
But
can probably draw it better that way than I can flat.
well, that's fine. Then flip your curve over, draw it like that, and flip it back. Right? You can do 90-degree rotations. That's all right. What was this? 0.8 something?
0.8644.
644. Okay. All right. So one more, and then we'll move on to new stuff. All right. 'Cause these are just way too much fun for me. So now let's find the probability.
One example, whole page.
Yeah.
This will be the homework work, right? Every homework question will take a full page. You should expect that, right? So the probability that the wages are less than 620 or greater than 780.
This one's also still in your calculator.
Shh.
Okay.
Don't give them the cheat.
I need the cheese.
Technically mine weren't, because I did the decimal point things and mine is not, so it's not the last man probably.
I can still have the chance.
So the cool thing about this, folks, is what did the question up above us ask? What did C ask for? Between 620 and 770, right? What did this question ask for? Less than 620 or greater than.
Still
So
the middle though, right?
I was asking for this piece. The next question is asking the rest of it, right? These are total opposites of each other. One of them is asking, what if I'm between 620 and 780? The other one is asking if I'm less than 620 or greater than 780. So if those two
That was
things,
a 7?
Hmm?
Go down, I thought that was a 2.
oh,
The last
I was
question
like
was
really confused, I was like,
770,
how
this
is
one's
that not
780.
the same as what we just did, because that's a 2.
was it 780 or 770? I don't even-
780.
This
Oh, is
one's
it?
780,
Oh.
the last one's 770.
So it's not quite the same. My bad, sorry.
But it's almost easier.
So how are we gonna do this one? Probability that x is less than 620 plus the probability that x is greater than 780. So notice, less than 620, less than sign, right? Greater than 780, greater than 780 sign. So just be careful with that. Read the words and make sure it translates into the right symbol. And then just do it one more time, right? You guys are gonna be savvy with this, whether you like it or not. using those Z's.
I don't even remember to change it to a Z.
It's a good idea.
Keep throwing down the X.
Nah, I'm gonna take it off of that. If you left this as an X, I'd give it to you. As long as you looked it up and the Z table is correct. Why is this one a little bit nice? Yeah, because they're opposites of each other, right?
Aren't you gonna change them though to the same?
Uh-huh.
Okay. Just making sure I'm doing that
And the cool part about it is that, remember what we did for the greater thans?
right. Multiply it by -1.
So here's the cheat. This is what Tequila likes, right? So there's that translation. And if you have greater than, you can switch it to less than. So you can convert this greater than to less than if you take whatever this number is and change the sign to a negative of it. Alright? And note that if this number were negative, it switches to being positive because negative and negative makes a positive, right? And so the nice part about it is that both of those numbers are exactly the same, right? So what's less than negative 1.6? Is this the 228 again, or is this?
0.548.
540.
Oh, is that the end answer?
No, I gotta multiply that by 3 now. We could do 1096.
So look for those shortcuts, folks, when you can take them as needed. Yeah. That's why I only asked for 4 questions from the summer. That section.
I'll say we need that
That's a lot.
note up there.
That's a lot.
Killing trees, man.
Yeah, I know, that's what you took, that's what school's all about, killing trees.
I think
Online
money
class.
Yeah. Well, you'd have to do it if it were online. Write it down, right? Alright, so that's 6.3.
Uno más.
Wait, so go to the next one?
So far we've been reading the table when we've been given a z value to find the probability. What happens if I give you guys the probability and it's your job to find the z value that makes that probability true? So, in other words, the probability that z is less than question mark equals something like point. Here, let me get one that's exact to start with. That is whatever. 0.1515. What is the question mark? So what value of z do you need to have such that the probability to be less than it is 0.1515?
-1.03.
Negative 1.03, that, is that
Or
right?
is it, then, okay, I was gonna say that mixed the numbers.
Sounds about right. I don't remember where I was looking now. Yes, so the idea, folks, is you look for that number in the table somewhere. wherever that number is in the table, if it's exactly in there, just read the z-value off, bingo, you're done. Right?
So, what if it's not exactly in there?
Great question.
I went in trouble.
So let's try a different one where it's not the same as in there. Probably that z is less than question mark equals 0.2000.
So would it be that, or would you have to divide by 2? Is that what you're looking for?
Nope.
Or do-
You just find the one that's closest, folks.
2005.20.
Find the z that gives closest answer.
So 0.84.
Was it
No, that's
0.84 or is it
a positive.
0.8? Or 0.8?
Negative one.
Yeah.
.85.
I know, it would be 0.084.
Which one is it?
I'm gonna go with 84.
Negative 84 sounds good.
85 plus 3 away, so 5.
So what are the two numbers that are just above and just below 0.2000 in the table?
0.2005.
There's 0.2005, that's the one just above. What's the one just below?
0.1977.
0.1977. Which of those two numbers is closer to 0.20000?
2005.
2005, right? This is 5 1,000 or 10,000ths away. This is 13 or 23 10,000ths away.
Yeah.
5 is obviously closer than 23. So this is closer. And so that's the value of z that you use. So in this case, z equals negative 0.84. Okay? And no, you don't have to do any extrapolation. I will forgive you of extrapolating. I will ask you to do one thing. If you are exactly halfway between values, then average them. So that's the only caveat that I will ask you to do, okay? If the number that you get is exactly halfway between two of the numbers, then definitely go ahead and tell me which one is that it's halfway between. So average whichever the two numbers are to get you halfway between. So in other words, let's do, what's the probability that z is less than question mark equals 0.9000? Now, again, do the same sort of thing, folks. Give me the number that's just bigger than it and the number that's just smaller than it.
8997 and 0 or 9015. Or
997.
0.9015.
9015 and 0.8997?
Yeah.
Alright, so which one's closer? 8997, what's that value?
1.28.
1.28. Alright. So now, which one is the one that's halfway in between? Oh, that's 95. Okay.
I have a question.
Yes.
How can there be 3 of the same answer?
Because the probabilities, once you start getting into really far away, the probabilities of certain values occurring is really, really small.
Oh.
So yeah, when you get into really high numbers, then it's tough. Because you can kind of pick. So how about 0.950. I think this is the one that's got one that's halfway between.
And a 0.950 on
9505 or 0.9495, right? And those two values are each the same distance from 0.9500, right? So this is where I would ask you to average the two of them together. And what's my z value going to be then? What's the top one? What's 0.9505?
1.65.
1.65, and what's the 0.9495?
oh, we average those.
Yeah, average the z's, not the.
I did that. I got 9.5. I'm
You're like, wait a
oh.
second.
Yeah,
Duh.
I'm brain farting here.
Okay.
All right, so note this is one of the few times where you can let z go to the thousandths place. Normally you don't. Okay, normally z only goes to the hundredths. Here's the one situation where it can slip into the thousandths, where you're exactly in between two, and you just average them together.
What do you wanna do if it's like that one where there's three of the same answer?
Pick your favorite. In other
You
words,
can't
I
really
would.
average them out then.
You could, yeah. I mean, that would potentially be a good idea. Usually, I would say if there's three of them, take them one.
So you wouldn't round it at all?
No.
Okay.
All right, and note, folks, if you look at table B, and you look at the bottom where it talks about critical values, what do you notice? That z equals 1.28. Right? Z equals 1.28. In that little table that talks about critical values, that's your first z number, right? That's for something that's called a 0.80 level of confidence, which we'll talk about in a little bit. And note, 90.95, 1.645, you go down two more boxes, and there's 1.645. Right? These are very standard numbers that you use when you're calculating statistical probabilities or statistical tests, and we will be using these numbers quite frequently. This is where those numbers come from, okay, is doing this sort of a calculation.
So what about the really fringe cases, like for 0.9997?
Where there's two or three of them?
There's 10 of them.
Yeah,
Does it matter?
No.
Are we ever going to get a question about those? Okay.
all right, so here's a twist now. What did I do to you this time?
It's greater than,
Ooh.
so now we have to take like the 1 minus whatever.
Mm-hmm.
Or we say it's greater than 0.39.
So the idea behind this, folks, is that you do the 1 minus thing, okay? You say 1 minus the probability z is greater than question mark equals 1 minus 0.3500. Right? And what is 1 minus the z greater than? That's the probability of z less than, right? That's the whole idea. And so this is 0.6500. And again, that should kind of make sense to some degree, right? Because if you think about it, I want to know what value of z has 35% that's greater than it. Well, that's the same z that has 65% less than it, right? So that's how you translate the greater than when dealing with these probability for finding z's. So what's the two values for 0.6500?
.6480.
0.6480, and what's the one above it? 0.6517. Which one's closer? 6517, because it's 0.17 away. This one's 0.20 away. What's this z value?
0.39. Can we just use the negative table for all of this?
You could have, yeah. If you'd have looked up negative,
Because that's actually what I did.
and did work.
Yeah.
That's fine.
By just looking up negative 3,500.
And then flip it to the positive. Because the nice part about it is that if you go over here, the negative, if this is z and then negative z, this would be 35%, this would be 65%. Symmetry plays the same sort of game.
Got it. Is this a bad habit that's going to come back to bite me?
No. That's just utilizing symmetry.
I got too many numbers already.
Alright, so let's see. Oops, I did it the other way around. Should be negative on this side, x on the other side. Whew. In other words, find the value of x such that the negative x on one side and the positive x on the other side, between those is 80% of your z curve. Alright? And so my advice when starting to get to these sorts of problems, folks, is draw a picture. Drawing the normal curve pictures really helps make these easier, okay? And again, your bell curve does not have to be pretty, all right? But the idea here is that I've got a negative x here and a positive x here, and in between it is going to be 80%, right? Because 0.8000, that's 80%. Why 10 and 10, Adam? Yeah, everything equals 100%, and since these are both the same values of x, the property of symmetry allows us to say, hey, this has to be 10%, this has to be 10%. So what can I simplify this problem down to? We'll just use this. Probability that z is less than negative x equals 0.10000. Find this x, right? Find that question mark. And so 80% of the curve is going to be between negative 1.28 and positive 1.28. All right?
So, because we already knew that 80% was already that number, would you just look down here at this?
Yes.
Okay.
And that's exactly why on that critical table, if you were looking at 80%, That is exactly what that level of confidence value is in the critical table, right? That's exactly what it's meant for, right? So if I gave you a similar problem and said, hey, what's the probability that negative x is less than z is less than x equals 0.9000? 1.645. Because now you can just use the critical values in table B. Because that's what those critical values are trying to do, is to try and find where the middle of the table has a certain percentage of your probability, right? And again, we will be playing around with these sorts of things a lot in the future, all right? All right, not bad? That is essentially the end of 6.3, or 6.4, sorry.
So 6.5, right?
And 6.5, it's really fast, folks. It takes like 2 minutes. You guys can handle it. You're big boys and girls.
Almost like so many cents for overtime.
No, you owe me. I'm going overtime.
No, that's not.
Yes, you're paying me to be here, remember?
Yeah, but you're going.
And now I'm giving you stuff for free. You should be paying me more. Bring candy next time.
It's like $20 an hour, something like that.
All right, so note, folks, that there are another set of tables, table C. In your books, it's on the opposite cover, so if you flip all the way over to the other side, you'll get the C tables.
I was about to flip this.
Hmm? So note that the C table is basically a slightly different variation on theme. These are T tables instead of Z tables. You will learn what these mean in chapters 8. We're not going to deal with them at all yet at this point in time. But what I want you to do is to be able to read the table, okay? First off, D period, F period, the far left-hand column of the table. These represent something called the degrees of freedom. You will learn what degrees of freedom mean in the near future, just bear with me. And then the rest of the table is all talking about area in one tail or area in two tails. So all of these values in the t-table are based off of either looking on one end, the other end, or in between, okay? And you can see the little pictures to the right of the table showing you an indication of what means what, okay? And so the idea here is that when you are asked to look up a certain value of t, you just have to find the right decimal point up there in the top. I know that the numbers are really small, but you can see 0.200, 0.100, 0.050 under the T at the very top of the table. It's tough to read, but they're up there. And those are the values that you are asked to look up. And this is just a lookup table, it's all it is. You don't do any calculations with this to determine where stuff is. You don't do any pluses or minuses or any of that kind of crap. This is all a very self-contained table. And we'll learn how to deal with it later, all right? But just realize that one tail is going to give you values of t that are less than or values of t that are greater than. And note that these two t's, since it's symmetric, it's still a symmetric table. So the value in one tail is either going to give you greater than the positive value or less than the negative value. You have to put the negative number in yourself onto these t-scores. And two tails just means that you've got t on one side, negative t on one side, positive t on the other, and half of your distribution is on each half, all right? So here, these alphas, these are alphas over 2. And that's just the number in the lower corner underneath the T up there at the table. Again, all I asked you to do for the homework on this section is to read the table. That's all you will do. So we won't do any calculations with any of this stuff at all until we get into chapters 8 and 9. So don't worry about it so much as you just know how to read the table. So you'll do a little bit of practice so that you get a chance, and then we will be good from there on.
What is a degree of freedom and why can you have an infinite amount of that?
When you have an infinite amount of degrees of freedom, a T turns into a Z. So that's kind of the idea behind it, is that infinite degrees of freedom means that you're a Z table. When you start losing degrees of freedom, you have to create a different value of your statistic. And that's what T is. And again, like I said, there's a big long explanation for the difference, and we'll get there. It has to do when your sampling size isn't big enough to warrant something being normal.
You ever seen the movie Real Genius with Val Kilmer?
Yeah.
Remember when the kid freaks out during setting? It's gonna be me.
You start screaming really loud. Start running.
Oh, he screams like over and over and just runs out the room. What does the other dude do? Just pulls up a book on his stuff.
Sits down where he was.
I think that was Val Kilmer too. He pulls up, he's like, wow, this spot's not taken.
Yeah, all I'm going to do is create the laser that shoots, a hole and everything. That's
Okay,
gonna be my
put it
goal.
through my head, please.
Yes.
Okay, I have 2 questions.
Okay.
Have you seen that movie? Oh.
I did this. Okay, this is lesson 4, section 12.
Yep.
When I stabbed them,
Oh, yeah. Well,
and then this gave me
I
a
forgot
really
what
funny
school
number.
they're at, but it's like a really
More like an E.
like they do
I didn't
some
know
crazy
that was
stuff on the
Because it was really, 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 really small.
Oh.
Yeah, it's like
The kid that
she
freaks
didn't
out,
have
he's the
any
one that makes
success
like
with
ice
her
out of
powers.
the tires.
Yes, exactly. So that
evaporates
almost will,
into gas
basically the
and
probability
shit
then is
like
that it will almost
Like,
not
Or
happen.
what is it?
Right, so if your E is
It's
like
the story
negative
is pretty much
58
follows
or
a
something like
14-year-old
that,
kid who goes to
that's a
college 'cause he's so smart.
really small
And
number,
Val
right? Because
Kilmer's, like,
Okay.
his buddy, his roommate.
So that's like reasonable
So
to
it's
have
when
like the
first
to the, it
meets him,
was
he
like
has,
to
like,
the
this little
negative
weird,
10
like,
or something.
you know,
yeah, that just means it's a really, really, really small
But
probability.
he's like,
Okay,
he's messing
can I
with like a
scan this
very
to you?
primitive
So I
one.
can like
And
fix
then it
this.
flies out the window
Yeah,
and
sure.
goes through everything.
Yeah,
He
yeah.
goes, oh my god!
But I got the
Would
rest
you
of
describe
them.
that
I was
as a
proud of
launch
myself.
problem or flow problem? If you have it like, if you
Yeah,
got
no, you
any,
can
like,
you can
free
scan and send those whenever you get them done.
Netflix and
That's fine.
stuff like that.
Those are the
They're
only
called
ones that you
Real Genius.
Okay. Yeah.
Well, I thought I
It is
was
a
doing
good
it right,
movie.
and I was like, I
Look,
don't know.
yeah.
And
I
then
guarantee
once
you'll probably
I
get
add
some,
them
like my
together,
girlfriend,
do I
she
have
doesn't
to get
know
a
science that much, so
percentage?
she doesn't get the jokes.
You can leave them as a
You'll get
rate.
that you'll probably get
Okay.
that over stuff. Oh yeah.
Okay, some of them I did. But I left the rate too.
That's one I gotta watch like once a year.
Real genius.
Real Genius.
I love when he has the popcorn go off in his house. I love
Oh
that
yeah.
too.
It's like, yeah, I love how they always use. He's like the same asshole in every movie.
Yeah.
Yeah.
He was very good at playing the part that he was meant to play.
Oh yeah. Just like what is it? Gary Busey plays a good psycho.
Mm-hmm.
Not quite anymore though, because he looks a little.
Well, he's lost the hard edge.
Yeah.
He's gotten smushy.
Exactly. You have a good weekend.
You do go.
I'll try.
Endeavor to persevere.
Indeed.